Problem 2 will be just continuation of problem 1. I remind you that for problem 1, we had the magnetic field, uniform magnetic field that was out of page, and we had a frame with resistance R, and we were pulling this frame out of the magnetic field with constant velocity V. For the second problem, I'll just make different choices, making sure that we understand what to do. Instead of the magnetic field pointing out of page, I will make it into the page. The magnetic field is into the page now. And let's figure out what happens. And we will follow exactly the same steps. Okay. First of all, we write the law, Faraday's law. This minus stands for Lenz's law. It tells us that generated current that will be generated in this loop will oppose the change in the flux of the magnetic field. And the flux, what I have here is, we call phi, it's integral B dot ds, the flux of the magnetic field. So the original external magnetic field that is given is into the page. The first question that we ask ourselves, why there will be current? Well, again, the same story. We pull it out, area decreases, area changes. We change the flux of the magnetic field in time, which means that we will generate current in this frame. The question is, which way will be this current? Let's think about it again. The original magnetic field is into the page. Okay, we move it out, which means that area of this loop that is inside the magnetic field decreases, area decreases. If area decreases, then flux decreases. Then B self-induced has to be in the same direction as the original magnetic field to oppose the change, to oppose the reducing flux. So B self will be in the same direction as B external. B self, I will use again blue for B self, has to be into this page. B self-induced magnetic field, the magnetic field induced by the current generated in this loop. To have B self into the page, which way should be the current? You have to use your right hand to figure it out. I use my left hand because you see my mirrored image. Okay, so what we do, let's try something. So let's assume that the direction of current will be, let's say, counterclockwise, as in the previous problem. Let's try current counterclockwise. Then I put my fingers along this current, and inside this loop, my fingers that show the direction of the magnetic field are coming out of this page, and we need it to be in the same direction as the original one, external one. We need it to be into the page. Obviously, this direction of current is wrong. So let's try the opposite direction. So now the direction of current that we try is clockwise. If current is in clockwise direction, you use your right hand, you put your thumb along current, you grab the wire, and what matters is the area in the magnetic, the area bounded by this loop, this area. We don't care about this area outside, just in. So I put my thumb, here my fingers come out, we don't care. But inside here, they go into the page. The direction of the magnetic field, self-induced magnetic field, will be into the page the way we want it. So the current, the direction of current generated by this motion of the loop, by this change of the magnetic flux, will be clockwise. We figure it out. Then we follow the steps. And I had to mention it from the very beginning that this was the solution for problem 1. So we need to make changes here, but we will follow the same steps. That's why I left it here. Step number 1, the direction of dr. Again, we will follow the convention, which means that we will go around this loop in counterclockwise direction. And if you go around this loop in counterclockwise direction, you put your right hand around the loop in counterclockwise direction. Your thumb shows the direction of ds, and ds in this case is out of the page. This is, I'll put it here, ds, area vector. Okay, so ds is out of this page, b is into the page, b is anti-parallel to ds, magnitude of one times magnitude of another one times cosine of pi, which makes it negative. I put minus here, and you know what? I will use different color for us to see where we made changes. So it is minus now because ds is out, b is in, they are anti-parallel. Minus dot product is minus b ds, minus s is still bls. Now d phi dt is minus this minus bl dx dt. What is the sign of dx dt? Same or different? We still, what is x one more time? X is part of this frame that is still in the magnetic field, and it changes. That's why I like to call it x. As we move it out, as we pull it out, x decreases. Smaller and smaller part of the loop is inside the magnetic field. So x decreases, dx dt is still minus v. Okay, so dx dt is equal to minus v, still, and minus plus. d phi dt is blv. Okay, now we come to the left-hand side of this equation. Integral E dot dr. Look, we go around the loop in counterclockwise direction, but current is in clockwise direction. Then J, current density, is in clockwise direction. Then electric field, that is rho J, is again in the clockwise direction. Electric field is down, we go up. They are anti-parallel. So, which sign of integral E dot dr we put here when we go across this resistor? We put minus. Because E is anti-parallel to dr. Minus here. Minus IR is equal to this absolutely crucial minus from Lenz's law. And then plus BLV. Okay, so minus is still here now. This is negative, minus BLV. But look at this, minus and minus. Of course, we get positive current because from the very beginning, we figure out the correct direction of current. So the correct direction of current in this case is clockwise, as we did from the very beginning. Now, let's check for a second the force exerted on this segment of this frame. So in the previous problem, we found the force. We understand that force exerted on this segment will be exactly the same as force exerted on this segment. They will cancel each other. The force exerted on this segment will be zero because here the magnetic field is zero. And we remember the expression for the force, dF is I dl cross B. Okay, so what I'm interested in this segment. What should be the direction of the force? According to Lenz's law, nature doesn't help you. So if I pull it out, the force should be in opposite direction. Is it the case? Let's check. So the current is up, which means that dl, or L in this case, the magnetic field is uniform, L is up, B is into the page. You use your right hand, you put your fingers along L, you bend them towards the magnetic field that is into the page, and then your thumb shows the direction of the force, and as expected, the force is to the left as it should be. So we solved the problem. It was just different, a little bit different setup in comparison with problem 1. This time we had the magnetic field into